A matrix is usually pictured as a rectangular array of numbers, but that picture is inexact. The array is only a way of drawing it. A matrix is really a function on the index set of row and column pairs, just as a sequence is a function. Being a function, matrices add place by place, which is just the addition of functions, and scalar multiplication works the same way. So all matrices of one shape form a vector space, a Cartesian space with a rather fancy finite index set. Theorem 4.1 handles the Cartesian case. Read the jth column of the matrix as an m-tuple. Then there is exactly one linear map whose skeleton is that list of columns, that is, one that sends the jth standard basis vector to the jth column. What is that map? It is the linear combination map. Multiply the jth coordinate of the input by the jth column and add. Written out coordinate by coordinate. This gives the familiar scalar equations, each output being a row paired against the input. Every linear map arises this way, so matrices and maps correspond by a natural isomorphism. A second one is being used quietly here. Reading a matrix as a list of columns identifies a function of two indices with an n-tuple of m-tuples. The rows admit another reading. The ith scalar equation is itself a linear functional, and coefficients times coordinates, summed, is the most general functional on a Cartesian space. So the m rows are the m functionals equivalent to the one vector-valued map. Now leave the Cartesian spaces. A general space has no ready-made coordinates, so ordered bases must be chosen. Theorem 4.2. With a basis fixed on each side, every matrix gives a unique map, sending the jth basis vector to the jth column combination. The proof only composes two isomorphisms. The matrix first gives a map between Cartesian spaces, and the two basis isomorphisms carry it over to V and W. Another view splits it in two. Each column fixes a vector in W, and those n vectors fix the map. The corollary finishes the point. Let x be the coordinate tuple of the input and y that of the output. Then the output equals the map applied to the input exactly when those scalar equations hold. With basis chosen, the abstract map is replaced by the equations. But one thing has to be remembered. A matrix is always with respect to chosen basis. On Cartesian spaces, a matrix is the natural alter ego of a map, but a map on a general space has no matrix of its own. Change the bases, and the same map gets a different matrix. A last lemma says how to read an entry off the map. Measure with the dual basis of W. Apply the kth dual basis functional to the image of the jth basis vector, and the number you get is the entry in row K, column J. Next time, the transpose, rank and products.